Today we are going to start on the topic magnetism and magnets and what are the categories of magnets and how our earth is also a magnet and how magnetic fields are produced and their effects on the real world. So let's start from the start. What are magnets? Magnets are essentially objects or metals which have the capability to attract or direct other metals towards itself. Now, a metal has two poles, north pole and south pole, and there are of two types. First is man-made or synthetic magnets, and the second is natural magnets. Synthetic magnets are also found in form of horseshoe magnets or many various forms of magnets, while natural magnets are very rare but found in deep minerals, rocks or salts. Now, let's talk about how our earth is a magnet. Our earth, okay, so first of all, let's start how the proposition of magnetic field even came for earth. Our earth has magnetic field lines which protect us from the suns and the uh, galaxies rays, and these magnetic fields are produced by ions which are present inside the earth's core. Various theories have been suggested on how the magnetic field of earth is produced, but the most uh, acceptable theories suggests that a magnetic field is produced from the ions inside earth. Other theories also suggest that earth itself has a giant magnetic inside it, which is not exactly the case, and it doesn't fit suitably because at such high temperatures no magnet can actually exist, and it also fails to explain why the moon doesn't have its own magnetic field. The idea that earth's ions have current, and they are always flowing and they produce current, and those current are actually produce magnetism or magnetic field lines or EMF induced current as well, and these magnetic lines are what cause the earth's magnetic field. Now let's talk about how the magnetic field lines on earth actually work. So before getting into the idea, we have to look at the fact on the geography of our earth. Suppose this is a ball, this is our earth, spherical earth, and this is the north pole. Suppose it's tilted, it's tilted at the angle of 22.5 degrees or north pole, and it's tilted like this, and this is the north pole, and there's a straight line going through. This is the geographical line, and it is also known as the geographical meridian. This is like the axis of rotation or the north and south pole we have designated as humans. So for example, this is north pole and this is south pole. However, the magnetic field lines of earth and the geographical north and south poles are actually very different. For example, this is the north pole, and this is, for example, the magnetic field line, magnetic equator, which is also called, or it's called a magnetic meridian. For example, this is the your sphere and earth, this is your geographical meridian. This is, for example, the uh, let's assume this, and this is sphere. This is like your what geographical meridian person. And suppose there's a magnet like this, like suppose it, and the magnetic field produced and go through like this is like your one pole, and this is your another pole, and these are the geographical poles. This is the north pole, this is the south pole, and vice versa. And now what happens is, this is the north side, and magnetic field lines come like this and act as the north side or north pole, geographical north pole, acts as a southern pole of the magnetic field. For example, for reference, here is the north pole, and magnetic field lines originate from the south pole and act as a north. You know how magnetic field lines in a magnet originate from the north like this, it goes like this. So the south pole acts as a north pole for the earth's magnetic field, and it goes like this, and it enters and it flows like this. And the difference between like geographical, like this geographical equator and this क्या कहते हैं, magnetic meridian is called the dip angle, sorry, equatorial angle, I think. Okay, so I checked again. It's called the magnetic declination, and this is the difference of angle between the geographical meridian and the magnetic meridian. And there is something called as angle of dip, which also exists. For example, the magnetic field act like this, like you know how it goes from this to this, and these are the lines. And suppose this is the horizontal of earth, like this is this, and magnetic field line come like this. So the slope produced, for example, these are the magnetic field lines, and this is the horizontal to, this is the magnetic field, this is the horizontal to, you know, the earth, this is horizontal to earth, like straight parallel, है ना? And this difference of angle is called angle of dip, and it is these angle of declination and angle of dip are both used to calculate the magnetic like you know, force of earth, and like the exact magnetic dipole moment of the earth. It is also known magnetic field is equal to bh cos theta for the horizontal, and bv is equals to bh sin theta for the vertical moment, and they comprise of, you know, the rectangular moment, you know, parallel theorem. And this is all there was to about earth's magnetism. And okay, so next we are talking about like the dipole moment of any two magnets or any magnet. So for example, this is a magnet in a magnetic field. Suppose there is a magnetic field down here, and this is like the your magnet with north and south pole, and the torque applied on it, for example, the torque, the force, this torque, the force to move it like sideways, this torque is like made of mb sine theta, where it is the vector cross of the m and b, where m is the magnetic strength and b is the magnetic field line, magnetic field strength. And this comprises of the torque which is associated with this magnet, and u, or the work done, is actually considered with minus mb cos theta, or you can say minus ka m dot product with b. And these are the torque associated and work done associated with the magnet. Now there is also a time period associated with the oscillation of this magnet, and this is associated with torque. And now the formula for this is T is equals to 2 pi under root I upon mb, where m is your magnetic strength, b is your magnetic field, and I is your, I think, current. Oh sorry, I is the mass of inertia. And this is about the oscillation and torque and work done of the magnet. Now there is something about the magnetic field line with respect to equatorial and axial position. For example, okay, so axial position would be like if two magnetic field or magnets are associated like this, an equatorial position, basically a 90-degree position, and the formula for that is u naught upon 4 pi m upon r cube. And the same goes for axial, where both are actually in a straight line or parallel to each other, and the formula for this goes as u naught upon 4 pi 2m upon r cube. Magnetic field intensity or magnetizing field intensity are two different things, where one is m and whereas one is h. Now what in a solenoid, for example, the magnetic field comes out to u naught ni. So that ni, the product of n and I, is equal to h, or magnetizing field intensity, whereas the magnetizing intensity, the difference is magnetizing field intensity is H and magnetizing intensity is M. The H is basically the field, like the force of the field, and M is like the intensity itself. Okay, and M is equal to magnetic moment divided by volume. And you can also consider this in the formula of density is equals to mass by volume, where you can get the volume and then calculate your magnetizing intensity through M. Now, what is this small m? Small m refers basically to dipole moment, and this is calculated in two forms. The first is where m is like the product of current into area, and the second is basically the same way how you calculate the dipole moment of current, or in chapter 2 capacitance or chapter 1 electric field intensity, where dipole moment is equals to q into 2l, or 2 times the distance, or basically q into the total distance between the two charges, and that is basically m, or m is equals to current into area. Force is associated with u naught upon 4 pi q1 q2 upon r cube, and magnetic field is associated with u naught ni, basically the same as in solenoid, and but this is only one aspect of the magnetic field, so there are two aspects here, and the total magnetic field comes out to u naught ni plus u naught m, the big one, the magnetizing intensity. And you know how like ni is equals to magnetizing field intensity, is comes out to be like u naught h plus u naught m. So basically u naught comes in common, and there's in this parenthesis m plus h, and that comes out to be your magnetizing magnetic field. Now there's also this relative permeability, which is like this form of u naught, which will come in later. And relative permeability is basically u naught upon basically the um value of u naught in the medium given divided by the value of u naught u in like vacuum, basically u naught u relative permeability is equals to u upon u naught, and this is later used to correlate with permeability and connects u relative permeability with m and h. And this is all for today, because it's already been 12 minutes and I have work to do.